Okay, so this is the start of Unit 6. We got the integration techniques unit to go with. I'm going to try to do these videos a little bit quicker or in a different format where I'll do just the rules here today, and then the next video it'll be the start of some examples, and then I'll do another video of a different type of example and so on, and try to break it up so that you can kind of focus more on whatever it is specifically rather than having a whole bunch together. But this is just all the rules here today, and then the examples be in the next videos. So, integration techniques. What is an integral? What is an antiderivative? Here it is. By definition, f of x, if f of x is the derivative of f of x, I mean, we would say by definition if f prime of x is the derivative of f of x, then f of x is called the antiderivative of f prime of x. So that's kind of what we do. But I wanted to throw in a different notation because you'll see this when they start talking about antiderivatives. They'll use capital F as your quote-unquote original function, and they'll say f of x was the derivative, but because f of x is the actual function you're starting with, capital F of x is the antiderivative. But I always like to think of it as f of x and f prime of x. So you'll see I'll change it up as we go along in the examples in the next couple videos, but I figured I would stick with the capital F and f. It doesn't mean much, just it falls through. Okay, so the first antiderivative rule that we want to know how to use is the power rule. It is the most common rule out there. This is the go-to. And it's simply this. If you have some function that has an exponent, all you do is you add 1, and I'm not going to prove any of this really. We're just going to use them. I mean, at some point, I'm sure you might see that in your university calculus where they'll say prove this, but it's pretty simple, but we're not going to waste our time. So all you do is you add 1 to the exponent this time. And if you think back to when we did derivatives, we minus 1 from the derivative, right? So we add 1, and then we divide by the end, by the new derivative. Okay? So there it is. Now the other thing about antiderivatives is you put a constant on there because, again, we don't know. There could have been a constant on the original function. Maybe I'll do a quick example just so you can see. Let's use the one that we have right above us there. Let's go if f of x equals 2x, and I want the antiderivative of that, I'm going to add 1 to the exponent, so 2x. This was a 1 here, so I'll add 1 to that and get 2, divide by that new exponent of 2, that cancels that out, and that's where we see f of x equaling x squared. Okay? So that would be a nice simple way of just following that rule that we just did. Now, the only problem is I said there's a constant, right? Now let me explain this. Plus a constant. You just put plus c. Now that'll come into play later. Okay? But right now, imagine that constant was a 3. I'm going to squeeze it in down here. It's going to make a mess of it, but that's okay. If I had that our function was x squared plus 3, and you did the derivative of that x squared plus 3, well, wouldn't the derivative be f prime of x would equal 2x plus 0? And I think you're going to go, yep, that's correct. So that constant doesn't mean much. It's just to tell the person that there could be a constant. It could be 0. It might not be there, but it is there. Okay, let's flip the page here and do the sign rule. Now, if I flip the page too fast on you, just back up and hit pause and finish writing the notes. Okay, sign rule. Well, let's think about this for a second. When we did the derivative of trig rules, like for instance, if I said take the derivative of cos x, the answer came out as negative sine x. So in this case, we're thinking backwards. So if this was sine x, then the original function must have been negative cos x. And again, like I said, in the next video, you'll see we'll do examples of this. Maybe not the next video, but the one after. This is just so we can get things out of the way. So there's the now if you've got that written down. Let's think about this. The derivative of negative cos, well, the derivative of cos is negative sine, so negative times a negative sine would be positive sine. So yeah, that makes sense. So there's the sine rule right there. The integral is. And these things you'll use quite often, and eventually they'll come old hat. Again, onto the cos rule, sort of the same idea, only this one here is going to be a sine kx all over k plus a constant. And I'll think about it out loud, and I'll say to myself, okay, well, what's the derivative of a positive sine x? Well, it's cos x. So that makes sense that the antiderivative of cos x would be the original function of sine x, plus your constant, of course. So, moving on. Ln rule. Again, if I flip the page, you can just back it up, hit pause, and write the rest out. So ln rule, well, this is pretty straightforward. If we know that the derivative of ln, for instance, is 1 over x, so the antiderivative of 1 over x would be simply ln. And because we can only take the log of a positive number, we say that it's an absolute value of x plus a constant. Oops, I should make that a bit bigger so it's a little bit more obvious. Plus a constant. So the antiderivative of anything 1 over a function is the ln of that function. And you'll see that come into play, especially when we do the technique of what's called partial fractions. Partial fractions, we use this rule lots. Okay, so when we get into partial fractions, which is going to be in a week or two time here from now, you'll start to see that one come out to play. And I throw a little twist in it, but it's pretty straightforward. The fifth rule we do is the Euler's number rule, or the exponential rule, and we know that the derivative of e to the x is just e to the x. So the only play on this one is that a that's involved, and we just say, well, the antiderivative of e to the x would be e to the x again, but with our a, and we just divide the whole thing by the a there, plus the constant. And you can go and make up your own example. I mean, if we had f prime of x was equal to e to the 2x, you could say f of x then must have been, using that rule, it's e to the 2x divided by 2. Now, to check it, just do the derivative of this guy. Do the derivative of that. Well, the derivative is going to be e to the 2x times the chain rule times 2. And of course, it's divided by that constant of 2. Well, the 2's cancel out, and there you go. It's true. Yep, it works. So that rule works beautifully as well. Okay, now the last one. This one here is a little bit different. This is the inverse tan rule. We don't use this a whole bunch. Again, we use it for mostly partial fractions. And when you get into like higher end calculus, you'll see it a bit more, and there's some places for it. But I like to put it in here because when we get into after substitution, I'll prove it when we do the substitution technique, or after we're done the substitution technique. But it's anytime you have something in this form, 1 over x squared plus a squared. Now, it doesn't have to be a 1. It could be a 2, 3, and you could factor that out. But it says this, that the antiderivative of something in that form will look like this. 1 over a inverse tan of x over a plus a constant. So that's the rule right there. Now again, you're thinking to yourself, well, how does that come about? Well, we'll wait and I'll show you how that all comes about when we know how to use substitution with the integration rules, integration techniques. Okay, so there's all the integral or the antiderivative rules that we're going to use for the very first assignment. Okay, and I'll show you some examples in the next video.